So, what are advanced computational hero methods? Advanced computational methods, or hero methods as we'll refer to them from here on, are methods that help us solve complex, nonlinear problems. Unfortunately, this course isn't exactly for beginners. If you're looking to get hands-on with machine learning or searching for a list of computational methods, this isn't the place for you. That's a bummer, and we're sad to see you go. But we look forward to seeing you back here when you're ready to tackle the meat and potatoes of hero methods. This course is for those of you who want to gain some intuition for how to successfully architect solutions that involve hero methods. We're here to teach the art of designing effective hero methods. Let's talk about brute force. In this case, that means the process of checking every possible value combination within a problem to gain a solution. There aren't enough computing resources in the world to evaluate large complex problems using brute force alone. And with that being said, trying to solve large complex problems via brute force is highly inefficient. Depending on the magnitude of the problem, this approach can take you years given the current limitations in computing power and architecture. Even for small and medium projects, the brute force approach could work, but it would be so inefficient that it would make your project non-viable. When we're talking about standard processes, think of something really easy to build, like a tool used to track time worked by an employee. Simple rules dictating the business requirements of the model can be used. Problems solved using hero methods are complex in nature and can't be modeled effectively using simple rules. In those cases, it's time to bust out the hero methods. To leverage any of these hero methods, we need ways to analyze and use the data available. This means abstracting underlying patterns in the data, properly generalizing the data, and simplifying the data to be useful. Perhaps most importantly, any method used must be able to perform its computation within a set amount of time and resources, and be organized in a formalism that can be understood by a computer. Standard computing efforts entail worlds that are fairly known, visible, and certain. Referring back to our time tracking application example, that app's design is highly visible to anyone that uses it, and most users quickly learn how time tracking works and can easily switch between apps. There's not much uncertainty. In contrast, complex problems involve worlds that are partially known, partially visible, or somewhat certain. Think of the partially visible world of poker. Hands are not fully visible to other players. In finance, there's a lot of uncertainty as to why the market moves as it does, and factors influencing change in the market can be a partial mystery. Take the example of how the market behaved when faced with the sudden pandemic. Lastly, the world can be partially known. For example, growing agriculture on Mars. The agricultural growth part we have experience with. The Martian landscape, not so much. We lack the know-how that comes from experience. In some problem scenarios, it can be impossible to arrive at the best solution. Many hero methods instead find a good enough solution that produces reasonably effective results while tolerating a small amount of error in the building blocks used. This approach is almost always necessary because the complexity of the mathematical functions used in the building blocks increases with the complexity of the subject of your model. After a certain threshold of complexity, the math becomes unsustainable, so you must find ways of simplifying that work while also tolerating some error. An example, finite element models, or FEM, have been unreasonably effective in mechanical engineering design, improving the safety of critical components and equipment like cars and planes, even though they tolerate a degree of error. Without FEM, the underlying calculus and differential equations would be so complex that it would be impossible to get any practical design done. FEM's effectiveness, despite the degree of error, is very similar in principle to how digital images are stored. If you zoom into a picture, ultimately you'll find A, it gets blurry, and B, the image starts to break up into pixels. These pixels are normally so tiny that assembled together they form very rich high-resolution pictures. Pixels are an approximation because the things they represent are obviously not made up of squares at the most minute level. We're willing to accept this error because they do the job of depicting an image incredibly well. Thankfully, due to the combined efforts of scientists, universities, R&D teams, labs, and other professionals around the world, we have a rich ecosystem of methods that solve complex problems. There are thousands of methods for solving any given problem. Keep in mind that it's almost mathematically impossible to evaluate every single method for solving a problem, because that process would outpace the available amount of computing resources and architecture available. This is much like brute force. It's impractical and time-consuming to try to evaluate every method that can be used to solve a problem. Even though we call it data science, we approach it in ways that seem non-scientific. We do what's worked before. We interpret things differently from one another. We have preferences and strong opinions, which are sometimes right. Power and Pareto laws apply to us. 98% of deep learning models are trained using 2% of available methods. We poke around in the dark and do things on hunches without having sound scientific reasoning. We're good at reusing and recycling ideas and methods. Perhaps data scientists should be called data artists. Design thinking, that is, learning through doing, is at the core of what we do. What's popularly thought of as science involves a great degree of creativity. There is no science without art. In this course, we want you to get started with understanding the creativity in design thinking. Think of this course like music school. Just like a new graduate of music school is not yet as well honed as a longtime musician, completing this course will not immediately place you on the same level as someone who's done this for years. The key to mastery for yourself is experience and hands-on application. Kato AI.